A black hole at the center of a small galaxy just produced something 140 times wider than our entire Milky Way. Not the galaxy itself, not a structure inside it. Something that erupted from it, stretched outward in two directions, and kept going for 23 million light years. To put that number somewhere useful, the distance from here to the Andromeda Galaxy, our nearest large neighbor, is 2.5 million light years. Porphyrion is nearly 10 times longer than that. End to end, this is not a galaxy in the way most people picture one. It is a pair of jets, plasma launched at near light speed from a supermassive black hole, shooting outward above and below, traveling farther than any structure produced by a single galaxy has ever been measured to travel. And the thing that produced all of it, the engine at the center, sits inside a galaxy smaller than the Milky Way. That is the paradox. A modest galaxy, an almost incomprehensible output. The jets reach 2/3 of the way into the cosmic void, not between galaxies, between superclusters of galaxies, out into the empty filaments and dark corridors of the cosmic web, the largest architecture in the universe. Until Porphyrion, no black hole jet had ever been shown to operate at that scale. The cosmic web was supposed to be purely gravitational territory, something shaped by dark matter and the slow accumulation of mass over billions of years. Porphyrion suggested the picture was missing something. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. When the discovery paper appeared in Nature in September of 2024, it carried a specific and uncomfortable implication. Supermassive black holes do not only shape the galaxies they live in, they can reach the cosmic web itself. They can push energy into the filaments that connect and feed entire galaxy clusters. If jets like this were common in the early universe, and there is growing evidence they were, then the structure of everything we can see may carry their fingerprint. That is what one black hole did. A black hole sitting inside a galaxy we can only see as it existed 7.5 billion years ago, when the universe was barely half its current age. The structure was named Porphyrion, after a giant from Greek mythology, a rebellious giant, one who fought the gods and refused to stay where he was put. The name fits. Before this discovery, the largest known jet system was Alcyoneus, also named after a mythological giant, also found by the same team, also using the same radio telescope network. Alcyoneus spanned roughly 100 Milky Ways. Porphyrion came in at 140. The record it broke had only stood for 2 years, and the record Porphyrion set was itself broken within months. Something is out there. A whole population of structures at this scale, invisible to previous generations of telescopes, finally showing up in surveys sensitive enough to catch them. We are not looking at a single exception. We are looking at the first catalogue entries of something that was always enormous and always there. This story involves radio telescopes spread across an entire continent, plasma travelling at nearly the speed of light, a fuel source that apparently never ran out, and a revision to how astronomers think black holes interact with the universe at its largest scales. The numbers in this story will stop making sense several times. That is expected. That is the point. Now look out, because we are about to go very, very far. In September of 2024, a paper appeared in the journal Nature that made a very specific and very large claim. The team behind it was led by Martijn Oe, an astronomer working out of the California Institute of Technology. They had found something. Not a new planet, not a new star, not even a new galaxy in the ordinary sense. What they described in that paper was a structure stretching 23 million light years from end to end. produced by a single supermassive black hole sitting at the center of a galaxy, billions of light years away. The paper did not bury the headline. The abstract stated the size, the figures showed the shape, and within days, the finding was moving through the astronomy community the way only a handful of results do, not as a curiosity, but as something that forced people to stop and reconsider assumptions they had not realized they were making. The object had an official designation. It was catalogued as J152932.16 plus 60153334 × 4, a sequence of numbers and decimals that tells you its coordinates in the sky, its position in the constellation Draco, and nothing at all about what it actually is. Designations like that are placeholders. They are how astronomers keep track of objects before those objects mean something. This one would not stay a placeholder for long. The team gave it a name. They called it Porphyrion, borrowed from Greek mythology, from the story of the Gigantomachy, the war between the giants and the Olympian gods. Porphyrion was one of the most powerful of the giants. In some versions of the myth, he was the king of them. He rebelled against the gods and had to be struck down by both Heracles and Zeus together. The choice of name was deliberate. The thing they had found was, by any reasonable measure, titanic. The name fit for another reason. In Greek myth, the giants were born from the earth, rooted in something ancient and enormous. Porphyrion, the structure, was built from something similarly ancient. The light captured in those observations had left its source 7.5 billion years ago. The universe, by best current estimates, is 13.8 billion years old. That means astronomers were looking at a structure that existed when the universe was roughly 6.3 billion years old, less than half its present age. The cosmos was younger, denser, and in certain measurable ways, more compressed. What Porphyrion was doing inside that younger universe, what it was reaching across, would turn out to matter enormously. But before any of that context became clear, the paper first had to establish the raw fact of the size. Previous surveys had found large jet structures before. Giant radio galaxies, that is the technical term for objects like this, had been catalogued going back decades. Most of the well-known ones spanned a few million light years at most. The record, such as it was, had been broken in 2022. The same team, led by OEA, had announced a structure called Alcyoneus, also named after one of the giants from the same myth, also found using the same radio telescope, spanning roughly 16 million light years. That was, at the time, the largest known structure of its kind. It held the record for 2 years. Then Porphyrion came in at 23 million light years, surpassing it by 7 million. That is not a marginal improvement. 7 million light years is 70 times the diameter of the Milky Way. The record did not inch forward. It jumped. Here is why that matters. When a record moves by small increments, it usually means the phenomenon is well understood and researchers are refining measurements at the edges. When a record moves in large jumps, it often means something else. It means the underlying population of objects is not fully mapped. It means the surveys and instruments being used have not been sensitive enough to capture the full range of what is out there. The jump from Alcyoneus to Porphyrion did not suggest that Porphyrion was a freakish outlier. It suggested that the tools being pointed at the sky were only recently powerful enough to see objects at this scale at all, and that more were waiting to be found. The paper made one additional claim that went beyond the record itself. Porphyrion was not merely the largest jet structure ever catalogued, it was the first black hole jet to reach the scale of the cosmic web. The cosmic web is the term astronomers use for the large-scale architecture of the universe, a vast network of filaments and voids, with galaxies strung along the filaments like beads on an enormous, three-dimensional thread. These filaments are among the largest structures in existence. Clusters and superclusters of galaxies sit where filaments intersect. Between them stretch regions called voids, enormous volumes where almost nothing lives. Porphyrion's jets extended 2/3 of the way into one of those voids, 2/3 of the distance from where galaxies cluster to where almost nothing exists. No jet had done that before. No single galaxy-produced structure had ever been confirmed at that scale. This distinction was not a technicality. It changed what had to be explained. Until Porphyrion, black hole jets were understood as local forces. Powerful, yes. Consequential for their host galaxies, certainly. Occasionally influential at the scale of a galaxy cluster. But they were not understood as objects that could reach beyond clusters entirely, that could push energy and plasma into the cosmic web itself. The paper from OEI's team argued, carefully and with data, that supermassive black holes do not only shape the galaxies they inhabit, they can shape the large-scale structure surrounding those galaxies. That is a different kind of influence entirely. It reaches past the local neighborhood and into the scaffolding of the universe. For most people, a paper in a scientific journal is an endpoint. The research is done. The result is published. In the world of astronomy, publications like this one are closer to ignition points. Within weeks, theorists were asking what kind of environment could sustain a jet for the billions of years required to reach this scale. Observers were re-examining archival data for signs of similar structures. The question of whether Porphyrion was exceptional or representative had no clean answer, and that open edge was exactly where the energy of the field moved. An enormous result with an unresolved implication is, for astronomers, more productive than a clean answer. Clean answers stop conversations. This one started several, and the conversations were not small. They touched on how the cosmic web formed, on how black holes in the early universe behaved differently than those in the local universe, on whether the standard picture of galaxy evolution needed revision at scales nobody had previously bothered to model. What they had found was not just a record breaker, it was something that did not fit cleanly into the existing picture of how black holes behave. The first thing to understand about Porphyrion is that it is not a galaxy in the way most people use that word. When most people hear galaxy, they picture something like the Milky Way, a vast spinning disk of stars, gas and dust bound together by gravity. Porphyrion is not that. What astronomers named Porphyrion are the jets, two enormous streams of plasma shooting outward from a single supermassive black hole in opposite directions, stretching 23 million light-years from tip to tip. The galaxy that produced them is just the engine. The jets are the event. To understand how that is even possible, you have to rethink what a black hole actually does. The popular image is simple. A black hole swallows things. Matter falls in, nothing comes out. That image is not wrong, but it is incomplete. Black holes, especially the supermassive ones sitting at the centers of galaxies, are not just consumers. Under the right conditions, they are among the most powerful ejectors in the universe. The key is what happens just before matter crosses the point of no return. When a supermassive black hole is actively feeding, the material falling toward it does not fall straight in. It has angular momentum. It spirals. As it spirals inward, it forms a flattened, rotating structure called an accretion disk. Think of water draining in a sink, but scaled up to billions of solar masses. The material in this disk is moving fast, colliding with itself, heating up to temperatures of millions of degrees. At these temperatures, the disk glows. It radiates enormous amounts of energy across the electromagnetic spectrum. A black hole with an active accretion disk becomes what astronomers call an active galactic nucleus, or AGN. Some AGN are among the brightest objects in the observable universe, outshining every star in their host galaxy combined. But brightness is not the strangest part. As the disk churns, it generates powerful magnetic fields. These fields do not sit still. They twist, they tighten, they thread through the innermost regions of the accretion disk and anchor themselves to the spinning black hole itself. This is where the ejection begins. A fraction of the infalling material does not make it into the black hole. The magnetic fields grab it and redirect it. Instead of falling inward, this material gets flung outward along the magnetic field lines, launching away from the black hole perpendicular to the disk, in two beams shooting in opposite directions. One goes up, one goes down. These are the jets. The material inside those jets is plasma, not gas in the ordinary sense. Plasma is what you get when matter is heated so intensely that electrons are stripped away from their atoms entirely, leaving behind a sea of charged particles. The plasma in a black hole jet is threaded through with those same magnetic fields that launched it, and as the charged particles spiral along those field lines, they emit radiation. This specific process is called synchrotron radiation. It produces radio waves at the low frequencies that telescopes like LOFAR are built to detect. It also produces the bluish visible glow you see in images of famous nearby jets. Every radio map of Porphyrion is, in a sense, a map of electrons spinning along magnetic field lines at near light speed across 23 million light-years of space. The ability to detect synchrotron radiation means that astronomers can observe jets even when they are completely invisible in ordinary light. This is one of the great advantages of radio astronomy. Where optical telescopes would see nothing but darkness punctuated by distant stars, radio telescopes reveal the jets in stark detail, tracing their paths across millions of light-years. The jets from Centaurus A, one of the nearest large radio galaxies, have been studied in extensive detail for this reason. Centaurus A's jets extend for about 1 million light-years, and they have taught astronomers much of what they know about jet structure and behavior. When astronomers first began to catalogue these radio sources, they did not always know they were looking at jets. Some of the brightest radio sources in the sky remained mysterious for decades. It was only through careful observation and comparison with optical data that astronomers pieced together the picture. Distant black holes were launching jets with enough energy to outshine their entire host galaxies at radio wavelengths. The power flowing through a single jet can be equivalent to the total energy output of 1 million stars. This staggering output depends on the black hole's mass and how quickly it is feeding. A more massive black hole feeding rapidly produces more powerful jets, but even smaller black holes can generate impressive jets under the right circumstances. The jets leave the black hole traveling at a significant fraction of the speed of light. In nearby galaxies where we can observe jets in detail, the plasma in some jets moves at more than 99% of light speed. The energy involved is staggering. The jets are not drifting. They are punching outward with extraordinary force, and in an actively feeding black hole like the one that produced Porphyrion, they maintain that force continuously as long as the black hole keeps feeding. At small scales, all of this is well understood. Astronomers have studied black hole jets for decades. They have mapped them in nearby galaxies, measured their speeds, analyzed their radiation, modeled the magnetic field structures threading through them. Jets that stretch a few thousand light-years, or even a few 100,000 light-years, fit neatly into the models. There are hundreds of known examples, and the physics is worked out well enough that scientists can predict what a jet should look like based on what they know about its host black hole. The trouble begins when the jets get very long. Picture a garden hose. Hold it at arm's length and turn the water on. The stream comes out straight, coherent, predictable. Now imagine that same hose extending not a few feet but all the way to the horizon. The stream has to maintain its structure across enormous distance, through varying pressures, through turbulence, across whatever material it encounters along the way. Real jets face an analogous problem. The farther a jet travels from the black hole, the more opportunities it has to interact with the surrounding intergalactic medium. The plasma is not moving through empty space. It is moving through a thin but real distribution of gas that fills the space between galaxies. Every interaction is a chance for the jet to lose energy, to slow, to wobble, to break apart. Most jets do eventually fall apart. The ones we observe spanning hundreds of thousands of light years are already impressive. The ones spanning millions of light years are exceptional. At those distances, something has to be holding the jet together. Some combination of initial power, magnetic field stability, and favorable surrounding environment. For a jet to reach 23 million light years, all of those conditions had to hold, simultaneously, for an almost unimaginable length of time. There is no agreed-upon mechanism that cleanly explains how jets survive to that scale. The magnetic fields threading through the plasma provide some structural coherence, acting something like a spine keeping the beam from dissolving into the surrounding medium. The ram pressure of the jet itself, the sheer momentum of the plasma moving outward, helps punch through any resistance. But both of these effects weaken with distance. Magnetic fields spread out. Momentum diffuses. The models that work for jets spanning thousands of light years start straining badly when applied to jets spanning millions. This is why Porphyrion was not just a record breaker. It was a problem. It was something the existing machinery of jet physics could not straightforwardly account for. Astronomers did not lack a general understanding of how jets form. What they lacked was a clear picture of how anything stays coherent across 23 million light-years of intergalactic space. The question nobody had a satisfying answer to was how a jet gets that big without falling apart. The galaxy responsible for all of this is not particularly impressive on its own. If you placed it beside the Milky Way, you would notice it is larger, heavier, more substantial, roughly 10 times the mass of our galaxy. But in a universe full of galaxies numbering in the hundreds of billions, 10 times the Milky Way is not a remarkable number. There are galaxies thousands of times more massive. There are clusters that contain thousands of galaxies each. By the standards of what exists out there, the host of Porphyrion is a solid, hefty object, and not much more than that. Its official designation is J152932.16 plus 600-1534 by 4, not a name that rolls off the tongue. Astronomers confirmed its identity using the W.M. Keck Observatory in Hawaii, matching it to the radio structure that LOFAR had revealed and pinning down its distance with spectroscopic measurements. That distance turned out to be 7.5 billion light-years from Earth. Write that number down somewhere and look at it. 7.5 billion light-years. The observable universe stretches roughly 46 billion light-years in every direction from where we are standing. This galaxy sits more than a sixth of the way to the edge of everything we can see. It is not in our neighborhood. It is not in our corner of the cosmos. It is deep out there, in territory that feels genuinely remote, even by the standards of extragalactic astronomy. Now consider what 7.5 billion light-years actually means in time. Light travels at roughly 186,000 miles per second. It circles the Earth more than 7 times in a single second. It crosses the distance from here to the Moon in just over a second. And yet light leaving that galaxy 7.5 billion years ago has only just now reached us. The photons landing in our telescopes tonight, the ones painting the faint radio image of Porphyrion across our data, started their journey before our Sun existed, before the Earth existed. The solar system formed roughly 4.6 billion years ago from a collapsing cloud of gas and dust. When the light now arriving from Porphyrion's host galaxy departed, none of that had happened yet. There was no Sun. There was no Earth. The material that would eventually build our planet was still scattered through space, unformed and waiting. Think about the other galaxies we know about and the light that reaches us from them. The nearby Andromeda galaxy, our largest galactic neighbor, sits only 2.5 million light-years away. When we observe it, we see it as it was before human beings existed on Earth, before our species had even begun its evolutionary journey. Yet Andromeda feels almost local compared to J152932.16 plus 61534.4. The vast majority of the galaxies we study lie somewhere between these extremes, near enough to seem accessible through our instruments, yet far enough to represent centuries, millions of years, or billions of years into the past. This graduated collection of temporal distances is what allows astronomers to piece together how galaxies evolve over cosmic time. We are not looking at a single moment in the universe's history, but rather a three-dimensional map where distance and time become interchangeable measures. The universe itself was roughly 6.3 billion years old when that light left. The universe is currently about 13.8 billion years old. So we are looking at this galaxy as it appeared when the cosmos was less than half its present age. The universe was younger then, smaller, denser. Galaxies were closer together. The web of filaments connecting them was more compressed. The whole structure of everything was tighter and more active than it is today. Here is something worth sitting with. The light you see from Betelgeuse tonight left that star around the year 1376. Knights were still riding through Europe. That light has spent over 600 years crossing space just to reach your eye. Now multiply that feeling by about 12 million. The light arriving from Porphyrion's host galaxy has been crossing the universe for 7.5 billion years. Whatever that galaxy looks like right now, whatever it is doing at this moment, we have absolutely no way of knowing. We cannot know. The information hasn't arrived yet. What we have is a snapshot, a single image frozen in time from an era so distant that the Earth did not exist to receive it. That galaxy may have merged with another galaxy by now. It may have been torn apart. The jets may have shut down entirely. The black hole at its center may have gone quiet. We are looking at the past, and the past is all we will ever have access to. This is one of the stranger features of astronomy that rarely gets acknowledged directly. We do not observe the universe as it is. We observe it as it was, at varying depths of time depending on how far away each object sits. Nearby stars we see as they were a few years ago. The Andromeda Galaxy we see as it was about 2.5 million years ago. Porphyrion's host we see as it was 7.5 billion years ago. The universe we think we know is actually a layered collage of different moments, all arriving at our instruments at the same time, none of them current. So what do we actually see when we look at this galaxy from 7.5 billion years in the past? A reasonably large elliptical-type galaxy, massive but not extraordinary, perhaps 70 billion solar masses, give or take. That estimate places it roughly 10 times heavier than the Milky Way. It was the kind of galaxy that, in a catalogue of millions of objects, would not make any list of the most dramatic or unusual. No exceptional brightness, no unusual shape that would flag it as something worth investigating. If you stripped away the jets and looked only at the galaxy itself, you might flip past it without pausing. That is what makes this situation strange. The object producing Porphyrion is not some colossal once-in-a-universe anomaly. It is a substantial galaxy, yes, but not an outlier. Not the biggest, not the brightest, not sitting at the center of some rare supercluster with exceptional resources. And yet, from somewhere inside it, a pair of jets extended outward until they had crossed 23 million light-years of space. The scale of what came out of that galaxy bears no obvious proportion to the galaxy itself. That mismatch is part of what made the 2024 discovery so difficult to immediately process. The product was far more impressive than the factory producing it. At the center of that galaxy sat a supermassive black hole. That is not unusual. Most large galaxies host supermassive black holes at their cores. Objects containing millions or billions of times the mass of our Sun, compacted into a region smaller than our solar system. The Milky Way has one. It is called Sagittarius A star, and it weighs about 4 million solar masses. The black hole at the center of J152932.16 plus 61534.4 was apparently far more active, fed by infalling material, channeling energy outward through those jets at a rate that maintained their structure across distances no jet had ever been measured to cross. The galaxy was the setting, the black hole was the engine, everything that Porphyrion is, all 23 million light-years of it, traces back to whatever was feeding that single black hole at the center of a galaxy we can no longer see as it exists today. To understand what 23 million light-years actually means, you need to start somewhere familiar and keep going until your sense of scale breaks. Start with the Milky Way. Our galaxy is roughly 100,000 light-years across, from one edge to the other. That number alone is staggering. Light moves at 186,000 miles per second. It circles the Earth 7 times in a single second. And yet a beam of light crossing the Milky Way from end to end would take 100,000 years to complete the trip. The galaxy you live inside is so wide that light itself needs longer than modern humans have existed to cross it. Hold that number, 100,000 light-years. That is your starting unit. Porphyrion is 23 million light-years across. That is not 23 million compared to 100,000 in a way that feels close. Do the division. Porphyrion is 230 times wider than the Milky Way. Some measurements put it at 140 Milky Ways, depending on exactly where you draw the outer boundary of the jet lobes. Either way, the ratio is brutal. You could line up every star-forming disk, every spiral arm, every dust lane of 140 galaxies identical to our own, stretch them end to end in a single unbroken chain, and you would still be looking at something roughly the same size as Porphyrion. That chain of galaxies would be Porphyrion. Now try a different comparison. The nearest large galaxy to Earth is Andromeda. On a clear dark night, you can actually see it with the naked eye, a faint smear of light in the constellation of the same name. Andromeda is 2.5 million light-years away. That distance feels cosmic. It is cosmic. Light leaving Andromeda right now will not reach Earth for 2.5 million years, and Porphyrion is nearly 10 times longer than that distance. You could pack the full gap between the Milky Way and Andromeda into Porphyrion's length 10 times over and still have room left. Here is one more. The local group is the name astronomers give to the cluster of galaxies our own Milky Way belongs to. It includes Andromeda, dozens of smaller satellite galaxies, and everything else gravitationally bound to our neighborhood. The local group spans roughly 10 million light-years. Porphyrion is more than twice that. A single jet structure produced by a single black hole is larger than the entire gravitational family of galaxies that contains our home. Try the scale model. Take the Milky Way and shrink it down to the size of a dinner plate. A standard dinner plate is about a foot across. At that scale, where would Porphyrion end? Not across the table, not across the room. At that scale, Porphyrion would stretch approximately the length of an American football field. You are standing at one end zone, holding a dinner plate, and the far edge of Porphyrion is in the other end zone, 100 yards away. The dinner plate is your galaxy. The football field is the jet. That comparison does something to a person if you sit with it for a moment. The visceral quality matters. Abstract numbers become concrete when translated into space you can walk. The football field helps your mind grasp something that mathematics alone cannot convey. Now bring in Centaurus A. If you have spent any time looking at images from professional observatories, you have probably seen Centaurus A without knowing its name. It is one of the most photographed objects in the sky. A massive elliptical galaxy with a dark dust lane cutting across its middle, surrounded by enormous radio lobes. Centaurus A is the closest active galactic nucleus to Earth, sitting about 13 million light-years away. Its jet system is famous precisely because of how large it is. Those jets span roughly 10 Milky Ways. Astronomers have studied Centaurus A for decades, partly because, at that scale, the structure is detailed enough to examine closely. Porphyrion is 14 times larger than Centaurus A, not slightly bigger, not a new record by a comfortable margin. 14 times. That multiplier is not merely incremental. It places Porphyrion in an entirely different category of cosmic object, operating according to principles that existing theory had not adequately described. Whatever made Centaurus A one of the most studied and visually dramatic objects in the night sky, Porphyrion did that and then kept going for another 13 times the same distance. The nearest famous giant jet system we have, the one close enough for us to study in detail, is a fraction of what Porphyrion achieved. Why does this matter beyond the spectacle of it? Because there are physical limits on how big jets are supposed to get. As a jet travels outward from its source, it is pushing through material. Not empty space exactly, but the diffuse gas that fills the space between galaxies. Every light year of progress takes energy. The jet is constantly being slowed, scattered, disrupted by the medium it is moving through. At some point, the models say, the energy runs out. The jet disperses. The lobes break apart and fade. The structure loses coherence. There is a ceiling. Porphyrion is through the ceiling. At 23 million light-years, this jet is operating in a regime where the standard models of jet propagation simply did not predict anything should survive intact. This is not a minor violation. The theoretical models were built on observations of structures far smaller, making Porphyrion's coherence a profound challenge to existing understanding. The gas between galaxies becomes increasingly tenuous as you move away from clusters and into the voids between superclusters. In one sense, this helps. Less resistance means the jet can travel farther. But even in near emptiness, a jet has to maintain its structure. The magnetic fields threading through the plasma have to hold their alignment across distances that dwarf anything astronomers had previously measured. The energy pouring from the black hole has to be consistent enough and sustained for long enough that the jets do not simply collapse before they reach full extension. Whatever Porphyrion's host black hole was doing, it did it long enough and hard enough to push plasma across 23 million light-years and leave coherent lobes at the far end. Those lobes, bright at their edges, are the evidence. They are not faint smears. They are structured, definable, with the hotspot morphology that marks an active, powerful jet system. The coherence of those structures is what matters most. A diffuse blob at this distance could be dismissed as noise or coincidence, but defined lobes with distinct hotspots indicate real physics operating at an unimaginable scale. The jet made it. All the way out there, it made it. There is something almost defiant about this. The universe imposes constraints. Objects operating at the edge of those constraints are interesting precisely because they reveal where the physics gets complicated. A jet half this size would be remarkable. A jet twice as large as any previous record would prompt serious investigation. Porphyrion is 40% larger than the previous record holder, which itself had shattered the record before that. Each time the outer boundary of what jets can do gets extended, the theoretical models have to stretch to accommodate the new reality. At 23 million light-years, the models do not just stretch, they have to be rethought. You are not looking at an exception at the edge of a known distribution. You may be looking at a category of object that existing theory had not properly accounted for. The same way Betelgeuse's dimming turned out to be a clue about something deeper happening in how the most powerful black holes interact with the structure of the universe around them. The size is not the end of the story. It is the question the story is trying to answer. Nothing produced by a single galaxy has ever been measured at this size, and that by itself is enough to demand an explanation. Not all black hole jets look the same, and the differences are not cosmetic. When astronomers began cataloguing radio galaxies in serious numbers during the mid-20th century, they noticed a pattern. Some jets faded as they extended outward. Others grew brighter toward their ends. This was not random. The shape of the emission was telling them something about the physics happening inside. A structure that brightens at its tips behaves differently from one that dims at its tips. That difference has meaning, and astronomers eventually built a system around it. In 1974, two British astronomers named Bernard Phaneroff and Julia Riley sat down with a catalogue of radio galaxies and sorted them by morphology. What they found was clean enough to name. There were two distinct families. The first had its brightest emission concentrated near the centre, close to the core, with the outer edges fading gradually into the surrounding medium. The second family was the opposite. Its outer lobes were the brightest parts of the entire structure, with sharp, concentrated knots of emission sitting at the very tips. Phaneroff and Riley called these two groups Class 1 and Class 2. Astronomers still call them Fry and FRII today, 50 years later, because the distinction has held up under every test since. The difference sounds like a bookkeeping detail. It is not. What the shape tells you is how much power the jet is carrying, and whether that power is enough to punch through the material surrounding the galaxy. Fry jets are the quieter ones. They launch from the black hole with real energy, but as they travel outward they slow down. They mix with the surrounding gas. They lose coherence. The brightness fades toward the edges because the jet is losing the fight against the medium it is moving through. Picture a garden sprinkler. Water fans outward in a soft arc, spreads wide, and falls without hitting anything hard. The energy dissipates, the pressure drops. Nothing at the edge is pushing back, because nothing is moving fast enough to reach it. FRII jets are different. They carry enough power to stay coherent over enormous distances. They drive through surrounding gas rather than blending with it. The jet maintains its structure, pushes outward, and eventually slams into the diffuse material at the far edge of its reach. That collision is where the energy concentrates. Particles pile up, magnetic fields compress, and the emission spikes. Those spikes are the hotspots. They are the brightest features of the entire system, sitting at the outer tips of the lobes like two lit fists at the ends of two very long arms. Think of a fire hose instead of a sprinkler. The pressure stays high all the way to the end, and when the water hits something solid, it hits hard. This morphological difference maps directly onto a difference in power. FRII galaxies are systematically more luminous in radio wavelengths than FRI galaxies. Their jets are not just longer, they are more energetic per unit length. They drive shockwaves into surrounding material at distances where Fry jets would have dissolved long ago. The boundary between the two classes is not perfectly sharp, and some objects sit in between, but the core distinction holds across thousands of catalogued systems. Shape predicts power. Power predicts reach. An astronomer looking at a radio image of an unfamiliar galaxy can read the morphology the way a geologist reads rock strata. The structure carries its history inside it. Over the decades since Phaneroff and Riley's original work, this classification scheme has become foundational to how astronomers interpret large-scale cosmic structure and evolution. The distinction between FRI and FRII objects reveals not merely morphology, but fundamental physics of jet production and propagation through intergalactic space. Astronomers discovered that FRII objects tend to inhabit more massive galaxies with denser central environments, suggesting a direct connection between jet power and host galaxy properties. This relationship has enabled researchers to use radiomorphology as a diagnostic tool for understanding both the black holes themselves and the broader cosmological contexts in which they operate. The FRI to FRII classification has thus evolved into one of extragalactic astronomy's most powerful and enduring interpretive frameworks. Porphyrion is an FRI, emphatically. Its outer lobes span 7 megaparsecs, which is 23 million light-years, and at the tips of those lobes sit the characteristic bright hotspots of an edge-brightened system. When you look at a radio image of Porphyrion, the center is relatively dim. The power signature sits at the edges, 11.5 million light-years out from the core in each direction, where the jets have spent an enormous stretch of cosmic time driving through whatever lay in their path. That morphology is not just a shape on a map. It is a statement about what the black hole at the center has been doing, how hard it has been running, and for how long. Classification systems like this exist for a reason. In astronomy, you often cannot directly measure what you want to know. You cannot fly out to a black hole and weigh it or time it or watch it operate. What you can do is measure the signature it leaves on the material around it. The shape of a radio galaxy is one of those signatures. An edge-brightened morphology with prominent hotspots tells you the central engine was powerful enough to drive a coherent jet across cosmological distances without losing the fight to the surrounding medium. It is the radio equivalent of a footprint. You see the shape and you know something about what left it, even if the thing itself is 7.5 billion light-years away and looks like nothing to the naked eye. There is also a relationship between FII morphology and environment. High-powered jets punch into the material around them, but they also inflate enormous lobes of diffuse plasma that spread outward from the hotspots. These lobes push back against surrounding gas. They heat it. They displace it. The jet builds its own cocoon of shocked material around itself as it travels. At the scale of a system like Porphyrion, that cocoon is not a small thing. It represents a colossal volume of gas that the jet has physically moved, heated, and rearranged across hundreds of millions of years. The shape of the system, those two edge-brightened lobes stretching in opposite directions, is the record of all that work preserved in the radio spectrum. What makes Porphyrion remarkable even among FII systems is not just the size, but what the size implies about maintaining power across time. A jet of 7 megaparsecs did not appear quickly. It required a continuous output sustained across timescales that are difficult to hold in the mind. At every stage of that journey, the jet had to stay focused, stay energetic, and keep driving. The FII morphology says it succeeded. The lobes are extended, the hotspots are bright, the structure is intact. Whatever was powering the black hole at the center of that host galaxy ran hard and ran long, and the edge-brightened signature stretched across 23 million light-years is the direct evidence of that sustained campaign. The hotspots at Porphyrion's outer edges are where the jets finally met resistance after traveling farther than any jet had ever traveled before. The discovery did not come from a single dramatic moment at a single telescope. There was no night when an astronomer looked up from a screen and gasped. No single instrument swung toward the right patch of sky and caught something no one had ever seen. What found Porphyrion was something slower, stranger, and in its own way more impressive than that. It was a map. The largest and most detailed radio map of the universe ever assembled. And Porphyrion had been hiding inside it the whole time. To understand how that map got made, you need to understand what LOFAR actually is. Most people, when they imagine a radio telescope, picture a single enormous dish, something like the Arecibo Observatory in Puerto Rico, a concrete bowl carved into a hillside, or the FAST telescope in China, 500 meters across and visible from space. Those instruments are real and they are remarkable. LOFAR is nothing like them. There is no dish. There is no bowl. There is no single structure you could point at and say, that is the telescope. LOFAR is a network. Its full name is the Low Frequency Array, and it is built from thousands of small, simple antennas spread across the Netherlands and into neighboring countries in Europe. Each individual antenna looks almost unremarkable. A set of crossed dipoles, low to the ground, not much taller than a person. The kind of thing you might mistake for an art installation or an abandoned science fair project. But the antennas do not work alone. They work together, and the way they work together is what makes LOFAR extraordinary. The technique is called interferometry. By combining signals from antennas spread across hundreds of kilometers, LOFAR effectively behaves like a single telescope as wide as the entire baseline between its outermost stations. The signals from each antenna are time-stamped precisely and sent to a central processor, where they are combined mathematically. Differences in the arrival time of radio waves at different stations encode information about where in the sky those waves came from. The wider the network, the finer the resolution. LOFAR's baseline stretches across much of northwestern Europe, giving it an effective aperture that no single dish could approach at these frequencies. And the frequencies matter enormously here. LOFAR operates between roughly 10 and 240 MHz. These are very low frequencies by the standards of radio astronomy, corresponding to wavelengths between about 1 meter and 30 meters. Most major radio telescopes operate at higher frequencies, where the sky is less cluttered with interference and many well-studied objects shine more brightly. The problem is that the extended lobes of black hole jets glow most intensely at low frequencies. This is a consequence of the physics inside the jets themselves. The electrons spiraling through the magnetic fields of a jet lose energy over time. The highest energy electrons fade first. What remains in an old or diffuse jet structure is a population of lower energy electrons emitting at longer wavelengths, lower frequencies. Previous radio telescopes, tuned to higher frequencies, were functionally blind to these faint, extended structures. The lobes were there, the signal was real, the instruments just could not hear it. LOFAR was designed specifically to operate where other telescopes could not. Its sensitivity at low frequencies is not a side feature. It is the point. When its survey teams began scanning the sky, they were looking at a part of the spectrum that had been largely unexplored at this level of resolution and depth. The structures that turned up were, in some cases, unlike anything catalogued before. The survey that found Porphyrion is called LOTSS, the LOFAR 2-meter sky survey. The 2 meter refers to the approximate wavelength at the survey's core frequency. Over years of observing, LOTSS compiled data across a significant portion of the northern sky, cataloguing radio sources with a sensitivity and resolution that no previous low-frequency survey had matched. When the results were processed, the catalogue contained 13.7 million individual radio sources. 13.7 million. Galaxies, jets, supernovae remnants, pulsars, and structures that did not fit neatly into any existing category. It was the most detailed radio picture of the universe ever produced. Porphyrion was one entry among those millions. Finding it was not obvious. A structure spanning 23 million light-years, seen from 7.5 billion light-years away, subtends a certain angle on the sky. That angle is large enough to be noticed, but identifying it as a single coherent object rather than several unrelated sources requires careful analysis. The team working with the LOTSS data had to distinguish Porphyrion's 2 giant lobes from the background noise of millions of other radio emitters. They had to establish that both lobes belonged to the same object, and then they had to figure out what that object actually was, meaning they had to find the galaxy at the center responsible for producing the jets. That is where the other telescopes came in. LOFAR could see the radio emission from the lobes, but pinpointing a host galaxy requires data at other wavelengths. The team turned to the Giant Metrowave Radio Telescope in India, known as the GMRT. The GMRT operates at higher radio frequencies than LOFAR's survey band, giving complementary data on the jet structure and helping to confirm that what LOFAR had detected was a genuine extended source rather than an artifact. Together, LOFAR and the GMRT gave the team a more complete picture of the radio morphology. For the optical side, they used data from DESI, the Dark Energy Spectroscopic Instrument. DESI is a survey instrument mounted on a telescope at the Kitt Peak National Observatory in Arizona, designed to map the large-scale structure of the universe by measuring the redshifts of tens of millions of galaxies. Its dataset contains detailed optical information about enormous numbers of objects across the sky, and it provided a candidate for the host galaxy sitting between Porphyrion's two lobes. Identifying a candidate, though, is not the same as confirming it. Confirmation required a spectrum. That spectrum came from the W.M. Keck Observatory in Hawaii, one of the most powerful optical telescopes on Earth. Keck's instruments can take the light from a faint, distant galaxy and spread it into its component wavelengths with enough precision to measure the redshift directly. Redshift is the stretching of light as it travels across an expanding universe, and measuring it tells you how far away something is. The Keck observation placed the host galaxy at a redshift corresponding to a distance of 7.5 billion light-years. It locked in the distance. Without that measurement, everything else was uncertain. With it, the team could calculate the true physical scale of what LOFAR had found. No single instrument in this chain could have completed the picture alone. LOFAR had the low-frequency sensitivity to detect the lobes. The GMRT sharpened the radio picture. DESI pointed toward the host galaxy. Keck confirmed the distance. Each step depended on the previous one. Take any piece away and the discovery either fails entirely or remains inconclusive. This is increasingly how astronomy works at the frontier. Not one telescope pointing at one object, but a coordinated sequence of instruments, each contributing what it does best, each handing off to the next. The structure had been sitting in the data the whole time, waiting for someone to ask the right question in the right part of the spectrum. The jets of Porphyrion are not made of anything exotic, which makes their scale even harder to explain. There is no mysterious substance here, no unknown particle. The material inside those jets is plasma, the same state of matter that fills the interior of stars, the same thing that flickers inside a neon sign, just taken to an extreme that the word extreme does not adequately cover. To understand what plasma is, start with a normal atom. A nucleus surrounded by electrons, orbiting at specific distances, held there by electrical attraction. Heat that atom enough, and the electrons get knocked loose. The atom stops being a neutral particle and becomes a charged one. The electrons fly free. What you have left is a soup of positively charged nuclei and negatively charged electrons, no longer bound to each other, responsive to magnetic fields in ways that neutral matter is not. That is plasma, and that is what Porphyrion is made of, from one end to the other, across 23 million light-years. The plasma inside the jets is not drifting. It is moving at speeds close to the speed of light, fractions of a percent below the universal speed limit. At those velocities, the particles carry enormous kinetic energy, and they do not travel in straight lines through the jet. They spiral. Magnetic field lines thread through the entire length of the structure, twisting through the jet like a coiled spring running from one end to the other. Charged particles moving through a magnetic field do not cut across those field lines freely. They wrap around them. An electron caught in a magnetic field spirals along it in tight loops, following the field line wherever it goes. In Porphyrion, those field lines run for millions of light years, and the electrons follow them the entire way. Here is where the physics produces something detectable. When a charged particle spirals along the magnetic field line, it accelerates. Accelerating charges emit radiation. The specific kind of radiation produced by relativistic electrons spiraling through a magnetic field has a name: synchrotron radiation. It covers a broad spectrum, from radio waves up through visible light, and the frequency of the emission depends on the strength of the magnetic field and the energy of the electrons. In visible light, synchrotron radiation from jets produces a characteristic bluish glow. In the radio part of the spectrum, it produces the low-frequency emissions that LOFAR was built to detect. Every radio map of Porphyrion is, in the most literal sense, a map of electrons spiraling along magnetic field lines. The light reaching those antenna arrays in the Netherlands is the direct physical product of charged particles corkscrewing through a magnetic structure 7.5 billion light-years away. The energy required to maintain this across 23 million light-years is not easy to put into ordinary terms. A single cubic meter of plasma moving at near-light speed along the magnetic field line carries a tremendous amount of energy. Multiply that by the volume of a structure 23 million light-years long and wide enough to register on radio maps, and the total energy content becomes a number that loses all intuitive meaning. Researchers working on jet energetics have to use units borrowed from cosmology just to write it down without the exponent becoming absurd. The power output of Porphyrion's jets has been estimated at the equivalent of several trillion suns running continuously. Not for a day, not for a year, for what must have been hundreds of millions of years at minimum to have built something this long. The problem with this picture is that plasma, at large scales, wants to come apart. Jets are not stable by default. The plasma inside a jet is subject to instabilities that are well understood in the physics of magnetohydrodynamics, which is the field concerned with how magnetic fields and conducting fluids like plasma interact. Kelvin-Helmholtz instability occurs at the boundary between the fast-moving jet and the slower material outside it. The shearing between those two regions generates ripples, and those ripples can grow into large-scale disruptions but shred the jet apart. Kink instability occurs when the magnetic field threading through the jet gets bent, and the bending amplifies itself, twisting the jet until it loses coherence. These are not theoretical edge cases. They are real processes that have been observed in jets far smaller than Porphyrion. Most jets do not survive them at large scales. Most jets dissipate their energy, spread out, and stop being jets long before they cover anything close to a megaparsec. Porphyrion covers 7 megaparsecs. It did not dissipate. Something kept it coherent across a distance where every known instability should have torn it apart. The answer, as far as researchers can determine, lies in the magnetic field itself. A jet threaded by a strong, well-ordered magnetic field is more resistant to these instabilities than one with a weaker or more tangled field structure. The magnetic field acts as a kind of internal scaffolding. It suppresses the growth of the kink instability by providing a restoring force that pulls the jet back toward alignment when it starts to bend. It controls the boundary mixing at the edges of the jet by organizing the plasma in a way that resists shearing. The magnetic field is, in the simplest terms, what holds a jet together. This is not controversial. What is not understood is how Porphyrion maintained a sufficiently strong and ordered magnetic field across this specific scale and over this specific time scale. Magnetic fields in plasma are not static. They evolve. They reconnect. They get tangled by turbulence. Keeping a magnetic field coherent over millions of light-years of jet is not simply a matter of switching it on at the source and watching it hold. The field has to be continuously sustained, replenished by the energy flowing out of the central black hole and threaded through the jet as new material is launched. The connection between the field structure near the black hole and the field structure at the outer lobes, 11 million light-years away on either side, is something that jet physics at this scale has never had to account for before. At smaller scales, models handle this reasonably well. At 7 megaparsecs, the models are being pushed into territory they were not designed for. There is another wrinkle. As the plasma moves outward from the black hole and the electrons radiate away their energy through synchrotron emission, those electrons lose energy. Old electrons, far from the source, have been spiraling for much longer and have radiated away a larger fraction of what they started with. This means the outer regions of a jet, in theory, should be populated by lower energy electrons producing lower frequency radio emission. Detecting these faint outer regions requires sensitivity at the lowest radio frequencies available, which is precisely what LOFAR provides, and why LOFAR found Porphyrion when other telescopes had not. The electrons in those outer lobes had been spiraling and radiating for an enormous amount of time. The signal they produce is faint, stretched to the lowest frequencies, but it is still there. The magnetic field was still there to keep them spiraling. Whatever kept those magnetic fields locked in alignment across 23 million light-years for billions of years is not a question anyone has fully answered. 2 years before Porphyrion, the same team had already broken the record once. In early 2022, Martin Oe and his colleagues at Leiden Observatory published a paper announcing the discovery of a radio galaxy so large it required a name from mythology to feel appropriate. They called it Alcyoneus. In Greek tradition, Alcyoneus was one of the giants, a son of Gaia, one of the most formidable opponents the Olympian gods faced during their war against the giant-born. The astronomers chose the name deliberately. What they had found was the largest known structure of galactic origin ever measured. Its jets stretched across roughly 16 million light-years end to end. That is about 100 Milky Ways laid in a line. The previous record holder had not come close to that. Alcyoneus did not nudge the record forward, it shattered it. To understand what that meant, you have to know what the field looked like before Alcyoneus arrived. Giant radio galaxies had been catalogued for decades. Astronomers had known for a long time that some black hole jets travel impressively far, but impressively far in the pre-LOFAR era meant something far more modest than 16 million light-years. The largest confirmed systems before 2022 spanned a few million light-years at most. Some of the most famous jet systems in the sky, like Centaurus A, the nearest example visible from Earth, stretch across roughly 10 Milky Ways. That was considered enormous. Centaurus A sits close enough that its jets have been studied in detail for generations. It appears in textbooks. It appears in documentary footage. It is the kind of object that feels definitive, like the upper boundary of what is possible. Then Alcyoneus came in at 10 times that scale, and the upper boundary ceased to exist. The host galaxy of Alcyoneus is located about 3 billion light-years from Earth. That is far, but not as far as Porphyrion. Its jets, like Porphyrion's, were detected in radio wavelengths at low frequencies. Like Porphyrion, its structure had been sitting unrecognized in the sky, too spread out and too faint at conventional wavelengths for earlier surveys to catch its full extent. LOFAR changed that. The low-frequency sensitivity of the array revealed the full reach of Alcyoneus's lobes in a way that no previous instrument could. What had been invisible became visible almost overnight. The paper describing Alcyoneus drew immediate attention. Here was a structure produced by a single galaxy that reached across a distance larger than most galaxy groups. Here was an object that raised the same uncomfortable questions Porphyrion would raise 2 years later. How does a jet hold together across that kind of distance? What does it mean for the surrounding environment when that much energy travels that far? The field had new territory to explore, and Alcyoneus opened it. Then something happened that almost never happens in the same research group twice in 2 years. The record broke again. When Porphyrion was announced in September 2024, it was not a different team working independently and happening to find something larger. It was the same group. Martin Oe, still at the center of the work, this time based at Caltech. The same LOFAR survey data, pushed further, filtered differently, scrutinized more carefully. Out of that same low-frequency sky, a second giant emerged. This one stretched 23 million light-years from lobe to lobe, 7 million light-years longer than Alcyoneus, roughly 140 Milky Ways instead of 100. Another Greek giant, another structure that had been sitting in the radio sky, undetected, until the right set of tools and the right set of eyes found it. The gap between these two discoveries is worth sitting with. 2 years. The same survey, the same team. 2 record-breaking structures found one after the other. In most fields, breaking a decades-old record once is a career-defining event. Breaking it again, immediately, with an even larger object is something different. It suggests the record itself was not a true ceiling. It suggests the ceiling had not yet been found. Part of what makes this pattern significant is what it says about the survey rather than the objects themselves. LOFAR's 2-meter sky survey, the LOTSS project, is not a targeted search. It is a wide-field mapping effort, accumulating data across enormous areas of the sky in the frequency range where extended radio lobes glow most clearly. As more of the sky gets covered at higher sensitivity, the population of detected structures grows. Alcyoneus was found in one part of that survey. Porphyrion was found in another. Neither was the result of a pointed search for giant objects. Both emerged from systematic data analysis of a survey designed to catalogue everything the sky was doing at low radio frequencies. This matters because it means the sample is incomplete by definition. The LOTSS survey was still mapping the sky when both discoveries were made. Large areas remained uncovered. The sensitivity at the edges of the survey is lower than at the centre. Processing pipelines improve over time, and structures that were missed in earlier runs sometimes appear in later analyses. Alcyoneus and Porphyrion are the largest objects the survey has produced so far. They are almost certainly not the largest objects the survey will ever produce. There is a name for this kind of situation in observational astronomy. It is called a detection bias correction problem. What you find depends on what you are able to find. Before LOFAR, the instruments available to survey the low-frequency radio sky simply did not have the combination of sensitivity, resolution, and sky coverage needed to detect structures at the scale of Alcyoneus or Porphyrion. They were not hiding, they were emitting radio waves the entire time. The technology to hear those waves across the full extent of the jets did not exist in sufficient form until LOFAR's survey data began accumulating. Alcyoneus and Porphyrion were not rare events that happened to be discovered. They were always out there, broadcasting. Astronomers just could not pick up the signal. What that implies for the broader population is something researchers are now actively working through. If 2 of the largest structures ever found came out of the same survey in the same 2-year window, the survey is clearly sampling a population of giant radio galaxies that previous catalogues systematically undercounted. How many more Alcyoneus-scale systems are sitting in the current data, unrecognized? How many more at Porphyrion scale? How many at even larger scales in parts of the sky not yet covered at full sensitivity? Nobody has a firm answer. The estimates suggest the population of known giant radio galaxies will grow substantially as the survey continues. Whether it will produce another record holder and how large that record holder will be is genuinely open. What the sequence of Alcyoneus and Porphyrion demonstrates is that the largest known structures in the universe are not stable discoveries. They are waypoints. Each one stands as the largest until the survey reveals something larger. Alcyoneus held that position for 2 years. Porphyrion took it. The survey kept going after Porphyrion was announced. The fact that both discoveries came from the same survey within 2 years of each other was less a coincidence than a signal that the survey was finding things nobody had been able to look for before. Galaxies are not scattered randomly through the universe. If you could step back far enough that entire galaxy clusters looked like dust specks, you would see something that nobody expected when astronomers first started mapping the large-scale structure of the cosmos. The universe has a shape. It is organized into a vast web. Enormous filaments of gas and dark matter stretch across hundreds of millions of light-years, connecting galaxy clusters at their nodes like threads connecting beads. Between those filaments sit voids, not empty exactly, but close. Regions of space so underpopulated compared to the filaments that matter there, is spread almost unimaginably thin. This structure, the filaments and the voids and the clusters at the intersections, is what cosmologists call the cosmic web. It is the skeleton of everything. The filaments are not a minor feature. They are among the largest structures in the known universe. A single filament can stretch for hundreds of millions of light years. They are the highways along which gas travels, funneling material down toward the dense galaxy clusters sitting at their junctions. When astronomers talk about galaxies being fed by cosmic filaments, this is what they mean. Matter flows along those threads, falling inward under gravity, eventually reaching a galaxy cluster and the galaxies inside it. The filaments shaped where galaxies formed, which galaxies grew large, and which ones stalled. They are not passive architecture. They are the plumbing of the universe. Now hold that picture in your head. A web of filaments, each hundreds of millions of light years long, with vast voids stretching between them. The scale of a single filament dwarfs anything a galaxy can produce. A galaxy, even a large one, is a tiny node sitting somewhere along one of those threads. The Milky Way, 100,000 light years across, is essentially a rounding error on the scale of a cosmic filament. No galaxy-scale process was supposed to reach filament scales. That was simply not how astronomers thought about the influence of individual galaxies or their central black holes. Local forces stayed local. The cosmic web was a gravitational phenomenon, shaped by dark matter and the initial conditions of the early universe. Black holes were not part of that picture until Porphyrion. Porphyrion's jets extend 23 million light-years from end to end. The lobes, the two enormous clouds of plasma sitting at the far reaches of each jet, reach 2/3 of the way into the cosmic void, the space between not just individual galaxies, but between superclusters of galaxies. This is not a measurement that sits comfortably in any previous category. Porphyrion is not reaching the edge of its host galaxy cluster. It is not filling the space between neighboring clusters. It is pushing into the emptiness between superclusters, the deepest kind of void the universe contains. 2/3 of the way into that void. That is not a local event. That is a cosmological one. Here is the piece that makes the raw number even more striking. When Porphyrion's jets were active, the universe was approximately 6.3 billion years old. The universe today is 13.8 billion years old. This matters because the universe has been expanding this entire time. The cosmic web has been stretching along with it. The filaments that existed 7.5 billion years ago were compressed, closer together. The voids between them were smaller. So when Porphyrion's jets were punching outward at that time, covering 23 million light years in a universe that was roughly half its current size, they were covering a larger fraction of the existing cosmic web than the same distance would represent today. The web was tighter. Porphyrion reached proportionally farther into it. A ruler that crosses 2/3 of a room covers more of the room than that same ruler in a larger room. The universe has since expanded that room considerably. This is why researchers describe Porphyrion as the first black hole jet to operate at cosmic web scales. Not because 23 million light years happens to match some arbitrary threshold, but because at the time and place this jet existed, it genuinely reached across a meaningful fraction of the universe's large-scale structure. It crossed from one kind of cosmic environment into another. It started inside a galaxy cluster and ended in the void between superclusters. Nothing produced by a single black hole had been observed to do that before. What does it actually mean to operate at cosmic web scales? Consider what the filaments do. They transport matter. They channel gas from the voids toward the dense regions where galaxies form and grow. They are the supply lines. A jet that pushes energy into those filaments, into the gas threading along those structures, is not just affecting its neighborhood. It is interfering with the plumbing. It is heating gas that was supposed to cool and fall inward. It is pushing material that was supposed to flow in one direction sideways. When astronomers talk about Porphyrion reshaping its environment, they are not speaking loosely. The jets were depositing energy directly into the medium that feeds galaxy clusters and the galaxies inside them. Whatever gas was flowing along the filament that Porphyrion's lobes reached into was being heated and disturbed by a process that originated 23 million light-years away in the core of a galaxy it would never interact with gravitationally. The implications are not small. If Porphyrion was not unique, and there is growing reason to believe it was not, then jets at this scale may have been operating throughout the early universe. The universe at 6 billion years old was a busy, dense place. Galaxy clusters were assembling. Filaments were channeling enormous quantities of gas. Supermassive black holes across the universe were being fed at high rates. If a meaningful fraction of them were producing jets on the scale of Porphyrion, then the energy they injected into the cosmic web would have been substantial. It would have heated gas across large volumes. It would have suppressed the formation of galaxies in some regions and perhaps altered which filaments could efficiently channel material in others. The distribution of galaxies we observe today, which parts of the cosmic web are populated and which remain sparse, might carry the mark of that activity. This is a genuinely new claim. The standard model of cosmic structure formation is gravitational. Dark matter collapses, pulls ordinary matter with it. Filaments form, galaxies condense at the nodes. Black holes were thought to influence their immediate surroundings, their host galaxies, perhaps their clusters, but not the cosmic web itself. Porphyrion broke that assumption by simply being too large to ignore. Its lobes sat in the void. The void is part of the cosmic web. There is no version of this in which the energy deposited there is a local event. What Porphyrion demonstrated, at the most basic level, is that the boundary between galaxy-scale physics and cosmic web-scale physics is not as firm as the textbooks assumed. A single black hole, given the right environment and enough time, can reach past its galaxy, past its cluster, past neighboring clusters, and deposit energy in the spaces between superclusters. That is not a local force. That is something operating at the scale of the universe's own architecture. Porphyrion was not just enormous by galactic standards, it was enormous by the standards of the universe itself. The numbers describing Porphyrion's energy output stop making intuitive sense very quickly. Start with something familiar. Our Sun, the star that warms every living thing on this planet, produces energy through nuclear fusion at its core. Hydrogen atoms are fused into helium under enormous pressure and heat, and the mass difference between what goes in and what comes out converts into energy. Every second, the Sun releases the equivalent of roughly 10 billion nuclear weapons going off simultaneously. That is the baseline. That is the unit of comparison. The Sun has been doing this for nearly 5 billion years without interruption, and to any human measure, that makes it almost incomprehensibly powerful. Porphyrion's jets outshine it by a factor of trillions, not millions, not billions, trillions. The combined power output of both jets flowing from the black hole at the center of that host galaxy is estimated at the equivalent of several trillion suns burning all at once. Not stars that size, not stars of roughly solar luminosity. Suns, specifically, all running simultaneously. If you lined up 1 trillion copies of our Sun and added them together, you would approach the energy budget of what one black hole was pumping into space through those 2 jets. The numbers do not translate into anything a human being can hold in their head directly. What you can do is work through the comparisons until the strangeness starts to land. Here is one way to think about it. The Milky Way contains somewhere between 200 and 400 billion stars. Most of those stars are smaller and dimmer than our Sun. Some are larger and brighter. When you add the full stellar population together, the entire galaxy combined produces an enormous amount of light and energy. The Milky Way is bright. You can see it from a dark field on any clear night, a pale band stretching across the sky, the combined glow of hundreds of billions of stars accumulated over 100,000 light-years of space. That is everything in our galaxy contributing at once. Porphyrion's jets, driven by a single black hole, outpace that entire stellar population by a significant margin. One object, two jets, more energy than every star in our galaxy combined, and doing it from 7.5 billion light-years away, in a host galaxy that was not even especially massive by the standards of the early universe. Now, the important question is where that energy comes from, because it is not fusion. Black holes do not fuse hydrogen. They do not burn fuel in any conventional sense. The energy driving Porphyrion's jets comes from something more fundamental. When matter falls toward a supermassive black hole, it does not drop straight in. It forms a rotating disk around the black hole, what astronomers call an accretion disk. The material in this disk spirals inward, and as it does, it releases gravitational potential energy. The closer matter gets to the black hole before crossing the point of no return, the more energy it sheds. The black hole's gravity is converting the position of mass into raw energy, and it does this with a ferocity that nuclear fusion simply cannot match. Nuclear fusion, the process powering every star in the universe, converts less than 1% of the mass of its fuel into energy. It is efficient by the standards of chemical combustion or anything a human engineer has ever built, but by the standards of fundamental physics, it wastes almost everything. Matter going through an accretion disk around a rapidly spinning black hole can, in theory, convert up to 40% of its rest mass into energy before crossing the event horizon. That is not a small difference. It is the difference between burning a candle and setting off a nuclear warhead, and then setting off that warhead versus something 40 times more potent again. Accretion around a black hole is the most efficient large-scale energy conversion process we know of in nature. What happens with that energy is where the jets enter the picture. Not all of the energy from infalling matter gets radiated away as light from the disk. A fraction of it, through mechanisms involving the disk's magnetic fields and the rotation of the black hole itself, gets redirected into two narrow beams pointing in opposite directions away from the disk. These are the jets. Plasma gets accelerated along those magnetic field lines and launched outward at near the speed of light. The fraction of the total energy budget that ends up in the jets rather than radiated from the disk depends on the specific conditions. But even a modest fraction of trillions of solar luminosities still represents an output that can carve through intergalactic space for tens of millions of light-years. The jets themselves emerge from the magnetic field structure that threads through the rotating accretion disk, a coupling between black hole spin and the field's geometry that remains not entirely understood in every detail. Yet observations of jets across many different black holes of different sizes suggest the mechanism is robust and universal. What is clear is that the jets do not constitute a continuous, steady beam in the way we might imagine a fire hose. Rather, they are channels of accelerated plasma whose properties vary across their extent, their intensity shaped by variations in the accretion rate and the black hole's magnetic configuration. The plasma moving through these channels is not particularly dense by ordinary standards. Captured and compressed, it would hardly fill your hand. What makes it significant is velocity and energy density, the sheer kinetic force of matter moving at relativistic speeds across scales that span galaxies. There is something else worth sitting with here. The jet did not reach 23 million light-years in a week. The plasma shooting out of the host galaxy's black hole has been traveling outward and building that structure across what physicists estimate must have been hundreds of millions of years, and possibly longer. Some estimates stretch toward a couple of billion years for a structure this large to accumulate. That means the black hole was not just producing this output for a moment. It was sustaining it for a span of time comparable to the age of complex life on Earth, or longer. Every year, for hundreds of millions of years, more plasma was being accelerated outward, more energy was being deposited, more of the jet was being extended into the surrounding space. The total energy that Porphyrion has put into its environment over its lifetime is something that defies any clean analogy. To keep a jet running at that output for that duration, the black hole needs matter continuously falling into the accretion disk. This is not a one-time event. It is a sustained process. The supply chain of material feeding that black hole must have been essentially uninterrupted across timescales measured in hundreds of millions of years. That implies something specific about the environment the host galaxy was sitting in, something we will come to. But what it tells you about the energy first is this: the black hole did not run out. Whatever was feeding it kept feeding it. The jets kept going. The energy kept flowing outward into the cosmic void, heating gas, sweeping through filaments, depositing power into structures on a scale that touches the cosmic web itself. A sustained output at this level kept running long enough to build something 23 million light-years across, requires a fuel source with no obvious limits. And that is where the story gets strange. The jets of Porphyrion did not travel 23 million light-years without doing anything. Every light-year of that distance represents plasma slamming into gas, magnetic fields threading through surrounding material, and energy pouring into spaces that were never quiet to begin with. The jets are not just moving through the universe, they are changing it. To understand what that means, you need to understand something about how galaxies and gas interact. Between galaxies, and threading through the filaments of the cosmic web, there is gas. Not dense gas, not anything you could breathe or even measure easily in a laboratory, but gas nonetheless. Thin, diffuse, stretched across enormous volumes. This gas is the raw material for star formation. For a galaxy to keep building new stars, it needs that gas to cool down, fall inward, and compress. Cooling is the key step. Hot gas does not collapse, it pushes back against gravity. It stays puffed up and does nothing useful. Cold gas falls. Cold gas forms stars. Now consider what a jet does to that gas. When plasma shoots outward from a supermassive black hole at near light speed, it carries energy, a tremendous amount of energy. When that jet punches into surrounding gas clouds, it heats them. It drives pressure waves outward through the medium, like a shock wave expanding from a detonation. The gas temperature rises. The cooling that was supposed to happen does not happen. The gas that was supposed to fall inward and form stars just sits there, hot and agitated, suspended against its own gravity. This process has a name. Astronomers call it jet feedback, or more specifically, radio mode feedback. It is not a minor or theoretical effect. It is one of the central mechanisms in modern galaxy evolution models. Without it, simulations of the universe produce too many massive galaxies that are too blue, too young, too full of stars. With it, the most massive galaxies shut down. They turn red. They go quiet. The feedback is real, and it leaves a signature in the galaxies we observe. The massive elliptical galaxies sitting at the centers of huge galaxy clusters are among the most striking examples. These are some of the largest galaxies in the known universe, containing hundreds of billions to trillions of stars. You might expect objects that enormous to be actively forming new stars constantly, fed by the enormous gas reservoirs surrounding them. They are not. Most of them are dead. Their star formation stopped long ago. The gas that should have cooled and collapsed was heated repeatedly by the jets of their central supermassive black holes. The black hole kept the gas warm. The galaxy stopped growing. This is not speculation. Astronomers have mapped the hot gas in clusters using X-ray telescopes and found cavities, bubbles, and ripples in it that trace directly to the jets of the central galaxy. The jets carved those holes. The jets drove those waves. The physics is well established at the cluster scale. The scale of that impact, however, operates in both directions. Heating the gas slows star formation in the central galaxy, but it also removes material that might otherwise flow outward toward other structures. The feedback does not merely suppress, it redirects and redistributes material. It alters the balance between gravitational flows and thermal pressure within these systems. Porphyrion changes the scale of the question entirely. A jet that reaches into the filaments of the cosmic web is not just affecting its host galaxy or its galaxy cluster. It is reaching into the spaces between clusters, heating gas that feeds not one galaxy, but potentially dozens of galaxies downstream. The filaments of the cosmic web are not passive structures. They are channels. Gas flows along them toward concentrations of mass. If a jet the size of Porphyrion heats gas inside those filaments, it is not suppressing star formation in one place. It is interrupting the supply line for a whole network of galaxies that depend on that gas to grow. Think of a river feeding a dozen towns along its banks. Block the river upstream, or heat it so that it evaporates before reaching those towns, and every settlement downstream feels the shortage. Porphyrion's jets extended 2/3 of the way into the cosmic void, reaching beyond their own cluster and pressing into the filamentary structures connecting the larger universe. The energy they deposited did not stay local. A heating event in a filament does not simply reduce downstream flow. It triggers cascade effects where heated gas creates pressure gradients pushing material away from cooling zones. The filament becomes not just a channel, but a barrier to essential processes. These effects compound substantially across cosmic scales. How much energy was actually deposited is difficult to calculate precisely. The jets have a total power output equivalent to trillions of suns. Even if only a fraction of that energy couples to the surrounding gas efficiently, the numbers are staggering. Enough energy to heat an enormous column of intergalactic medium. Enough to push gas out of filaments and into the voids where it cannot be retrieved easily. Enough to alter the growth trajectories of galaxies that never had any direct contact with the jet itself. This is what astronomers mean when they say Porphyrion may have influenced the evolution of the universe more broadly than anyone had assumed. Not a figure of speech, an accounting of where the energy went. The jet put energy into the environment. That energy affected gas temperatures. Those temperatures affected cooling rates. Those cooling rates affected which galaxies got new material and which ones were cut off. At Porphyrion's scale, this chain of cause and effect reaches across a region larger than galaxy clusters, larger than the spaces between them, up to the scale of the cosmic web itself. There is a subtler implication here that researchers are still working through. Porphyrion existed when the universe was roughly 6.3 billion years old. The universe at that time was smaller, denser, more compressed. The filaments of the cosmic web were closer together. A jet that reached 23 million light-years across the sky covered a proportionally larger fraction of the cosmic structure than the same jet would today. The early universe was more tightly packed, and feedback operating in that environment touched a larger share of the total available gas. If jets like Porphyrion were not rare in the early universe, if they were common, then the feedback they produced was not a local story. It was a story about the whole universe, playing out across its most formative period of galaxy growth. That word common carries a lot of weight. Before LOFAR began producing surveys of the sensitivity it has achieved, astronomers did not have a clear census of how many jets at this scale existed. The discovered population was small. The assumption was that such structures were exceptional. Porphyrion and the discoveries immediately surrounding it are beginning to challenge that assumption. If the survey keeps producing giants, then what looked exceptional may turn out to be a category. and a category of jets operating at cosmic web scales during the epoch when most of the universe's stars were being formed changes the calculation significantly. The galaxies we observe today grew up in an environment shaped in part by this feedback. Which ones received a steady supply of cold infalling gas, and which ones did not, is partly a gravitational story. But it is also apparently partly a story about where the jets were and how large they got. If this kind of feedback operated across cosmic web scales in the early universe, then the distribution of galaxies we see today may carry the fingerprints of black holes we have not yet found. The most unsettling thing about Porphyrion is not its size, but the duration required to build it. When astronomers look at the jets and try to work backward, the numbers become uncomfortable. Jets do not travel at the speed of light. The plasma moves fast, close to it in some regions, but the process of building a jet structure across millions of light years is not instantaneous. It is geological. Physicists working through the models estimate that reaching a scale of 23 million light-years would have taken somewhere between several hundred million and a couple of billion years of sustained output. That is not a burst. That is not a flare. That is a black hole that essentially never stopped eating for longer than complex life has existed on Earth. Think about what that requires. Every day, for what may have been a billion years or more, material had to fall toward the center of that galaxy, get caught in the accretion disk, and get redirected outward into the jets. The engine never stalled. The fuel never ran out. Something kept feeding it. This does not happen by accident. When astronomers look at the most extreme jet systems in the known universe, there is a pattern. The largest jets tend to come from galaxies sitting in the richest environments. Dense knots of gas, thick filaments of the cosmic web funneling material inward, galaxy clusters wherein falling matter is abundant and continuous. The host galaxy of Porphyrion, at roughly 10 times the mass of the Milky Way, was a substantial object. It was not the most massive galaxy in the universe at the time it existed. There are galaxies heavier by a significant margin. But mass alone does not determine how well a black hole feeds. Location matters. The supply lines matter. A black hole sitting at the junction of several dense cosmic filaments has access to material that a more isolated galaxy simply does not. The evidence from Porphyrion's scale strongly suggests its host galaxy was exceptionally well positioned. It was not just massive, it was connected. The cosmic web at that epoch, 7.5 billion years ago, was more compressed than it is today. The universe was younger, smaller, and the filaments threading through it were closer together. Gas densities in those filaments were higher. The highways feeding galaxies were more active. A galaxy sitting inside or near a dense node of that web would have had a nearly continuous supply of raw material arriving from multiple directions. This is the environment that can sustain a jet for a billion years. Strip that galaxy of its location, move it to a void, cut off the incoming gas, and the jets would eventually starve and fade. Location is not a minor variable here. It may be the central one. Here is where the story gets stranger. The jet itself may have been shaping the conditions that kept it running. As Porphyrion's jets traveled outward, they were not passing through empty space. They were moving through gas. Hot plasma punching into that surrounding medium transfers energy into it. The gas heats up. Heated gas does not cool easily. Gas that cannot cool cannot collapse. Gas that cannot collapse cannot form stars, and it cannot fall inward toward the galaxy's center as efficiently either. This is the mechanism astronomers call jet feedback, and it cuts in two directions. On one hand, the jets heat the surrounding gas and suppress what would otherwise happen to it. On the other hand, the same heating can regulate the inflow rate, keeping the supply of infalling material steady rather than letting it all dump in at once and overwhelm the system. What this produces is something close to a self-regulating engine. The black hole eats. The jets fire. The jets heat the surrounding gas. The heated gas falls inward more slowly and more steadily. This controlled infall means the black hole keeps receiving fuel at a manageable rate rather than in violent, unpredictable bursts. The jets stay on. The cycle continues. This is not a theory invented to explain Porphyrion. Versions of this self-modulating behavior have been observed in other radio galaxies and in galaxy clusters where black hole feedback keeps the central gas from cooling catastrophically. But Porphyrion operates this mechanism at a scale that makes the local examples look modest. The same feedback loop, running for long enough, in a rich enough environment, produced something that extended across a significant fraction of the cosmic web. The question of why some black holes produce jets at all, while others of similar mass do not, is one of the open problems in astrophysics. The spin of the black hole matters. A rapidly spinning black hole can extract energy from its own rotation and channel it into the jets through a process involving the twisting of magnetic field lines near the event horizon. Porphyrion's black hole, to have sustained output at this level for this long, was almost certainly spinning fast, possibly near the maximum allowed by physics. A slowly spinning black hole bleeds less energy into the jets. A fast spinner can sustain them. But spin alone does not explain Porphyrion. Spin sets the efficiency of the engine. The fuel supply determines how long it runs. What the full picture suggests is a convergence of conditions. A massive galaxy, sitting in a dense region of the early cosmic web, with a rapidly spinning supermassive black hole at its center, surrounded by abundant gas flowing in from multiple filaments, and a feedback loop keeping the infall rate stable enough that the engine never choked and never starved. Remove any one of those conditions and you likely do not get Porphyrion. You get something smaller, something that ran out of fuel early, something that dissipated before it reached its observed scale. The fact that we found one of these structures does not mean they are everywhere. It may mean that the precise combination of conditions required to build them is rare, and LOFAR was finally sensitive enough to find one when it looked carefully enough across a large enough portion of the sky. There is also the question of timing. The universe at 6.3 billion years old was going through a phase when supermassive black holes were, on average, more active than they are today. The era of peak quasar activity, the era when the most powerful engines in the universe were running at full capacity. Porphyrion was born in that window. It had access to the fuel-rich conditions of an early, denser universe, and it had the location and the spin to make use of them. It is not an accident that one of the largest structures ever produced by a single galaxy comes from this particular period in cosmic history, rather than from the universe as it exists today. A jet that feeds for that long is not a random accident. It is the product of a galaxy sitting in exactly the right place at exactly the right time in cosmic history. For decades, the accepted picture was that supermassive black holes were local forces. They governed their host galaxies. They heated the gas in their immediate clusters. They punched jets into the surrounding medium, and the medium pushed back, and that was where the story ended. The influence of a black hole, however enormous, was thought to be fundamentally contained, a neighborhood phenomenon in a universe of neighborhoods. Porphyrion changed that assumption in a specific and measurable way. The jets of Porphyrion did not stop at the edge of their host galaxy. They did not stop at the edge of the galaxy cluster surrounding it. They pushed 2/3 of the way into the cosmic void, the near-empty space between superclusters, and they did it 7.5 billion years ago, when the universe was smaller and those voids were more compressed. What this means is that the energy from a single supermassive black hole reached structures that were supposed to exist entirely outside its domain, not its galaxy, not its cluster, the filaments themselves, the skeleton of the universe. To understand why this is significant, you need to hold two ideas at once. The first is that the cosmic web, The vast network of gas filaments and dark matter threading through the universe was thought to be shaped almost entirely by gravity. Dark matter collapsed first. Gas followed. Galaxies formed along the filaments where density was highest. The voids emptied out. This picture is gravitational from start to finish. Gravity built the web, and the web determined where galaxies grew. Black holes were passengers in this story, not architects. The second idea is that Porphyrion suggests this picture is incomplete. If a single black hole could push jets across a meaningful fraction of the filament scale, then black holes were not just passengers. They were adding energy to the web itself, heating gas in regions that gravity was trying to pull together, pushing back against the very process that was building large-scale structure. That is not a minor footnote. That is a revision to the foundational model of how the universe assembled itself. Here is the practical consequence. Gas in the cosmic filaments is the raw material for future galaxies. When that gas cools, it falls into potential wells and forms stars. When something heats it, the cooling slows, the infall slows, and star formation stalls. Galaxy clusters contain this process through what astronomers call radio mode feedback. Jets from central black holes reheat gas that would otherwise cool and collapse. But that feedback was assumed to stay inside the cluster. Porphyrion's jets reach the filaments feeding the cluster from outside. That is a different scale of intervention entirely. Think about what that means for any galaxy trying to form along a filament that a Porphyrion-scale jet was threading through. The gas it needed was being heated by energy from a black hole in a different galaxy entirely, in a different part of the web. The formation history of that galaxy was being written, at least in part, by a source it had no direct relationship with. A black hole 23 million light-years away was influencing its future. Nothing in the standard model of galaxy formation had room for that. The researchers behind the Porphyrion discovery were careful about how they stated this. They did not claim that black holes built the cosmic web from scratch. What they said was that supermassive black holes do not only hold sway over the galaxy, but also over the cosmic web that surrounds them. That is a narrow, defensible claim. But the implications widen quickly when you ask the obvious follow-up question. If one black hole did this, how many others did too? The answer is not yet known. What is known is that Porphyrion was observed at a time when the universe was roughly 6.3 billion years old, less than half its current age. The early universe was more active. Supermassive black holes were feeding faster, generating more powerful jets across a more compressed and denser cosmic web. If jet systems at Porphyrion scale were common in that epoch, then the energy they deposited into filaments and voids was not a local anomaly. It was a widespread influence operating across the observable universe at exactly the time when the large-scale structure of the cosmos was still being decided. The implications of this timing are profound for understanding cosmic evolution. In that earlier epoch, galaxies were still assembling from primordial material, and the density of the cosmic filaments was significantly higher than today. The jets from black holes like Porphyrion would have encountered gas that was actively flowing along these filaments, material still in the process of cooling and contracting under gravity. By introducing heat at this critical moment, supermassive black holes could have fundamentally altered the trajectory of structure formation. The timing places this feedback mechanism precisely when the universe was transitioning from rapid growth to slower accretion rates. Early intervention at this stage would have had cascading effects, rippling outward through the web and affecting the entire network of cosmic filaments. This is what makes the discovery difficult to absorb. It is not just that one object was unexpectedly large. It is that the existence of that object opens a question about the entire architecture of the universe. The arrangement of filaments and voids we see today, the reason galaxies cluster here and not there, the reason certain regions of space are rich with structure and others are nearly empty, may carry the signature of black hole activity from 7 or 8 billion years ago. activity that left no obvious visible trace, activity that only became detectable when a radio telescope sensitive enough to pick up faint emission at low frequencies finally scanned the right patch of sky. Astronomers working on large-scale structure simulations now face a genuine question about whether their models are missing a term. The standard cosmological framework, dark matter, dark energy, gravity, and initial conditions from the Big Bang, produces a cosmic web that matches observations reasonably well. But reasonably well is not the same as exactly. There are tensions in the model. There are regions where the observed distribution of galaxies does not quite match the predictions. Nobody is claiming that Porphyrion scale feedback explains all of these discrepancies. But the possibility that widespread black hole jet activity in the early universe deposited energy into the web at scales the simulations never included is now a serious subject of investigation rather than a fringe idea. What changed with Porphyrion is not just the record. What changed is the scope of the question. Before Porphyrion, the question was how black holes regulate their host galaxies. That question still matters. It is still being studied, but now there is a second question sitting next to it, larger and harder to answer. Whether a black hole can influence not just a galaxy, not just a cluster, but the filaments connecting clusters to each other. Whether the energy from objects this small, measured against the scale of the universe, could have left marks on the larger structures that exist. The question now being asked seriously for the first time is whether the large-scale architecture of the universe, the web of filaments and voids that everything we know lives inside, was shaped in part by objects no bigger than a solar system sitting at the centers of galaxies. Porphyrion did not hold the record for long. Sometime in the same year that Martin Oey's team published their findings in Nature, another radio galaxy quietly entered the picture. Its designation is TXS 0033 plus 252. It does not have a mythological nickname yet. It does not carry the name of a rebellious giant or a creature of ancient legend. It is a string of numbers and letters in a catalogue that most people will never read. But what it has is size. Researchers examining radio survey data identified its jet structure as spanning approximately 8 megaparsecs, which converts to roughly 26 million light-years from end to end. Porphyrion, at 7 megaparsecs, had stood as the largest known jet structure in the universe for a matter of months before something larger turned up. The record had already been broken once when Porphyrion surpassed Alcyoneus in 2024. Now it was broken again, almost immediately. That is a strange thing to sit with. 2 records in a single year, both involving structures that dwarf anything previously catalogued, both arriving in such rapid succession that the first barely had time to be absorbed before the second appeared. The obvious question is whether this is coincidence. It is not. The pace of these discoveries is not the product of luck or a sudden burst of astronomical inspiration. It is the product of instruments finally operating at the sensitivity and frequency range required to see this class of object at all. Before LOFAR class surveys became available, giant radio galaxies existed in the universe the same way they exist now. They were out there. They were enormous. Nobody could find them, not because nobody was looking, but because the tools available were not built to detect structures this faint and this extended at the radio frequencies where jet lobes glow most clearly. Porphyrion and TXS 0033 plus 252 did not appear because the universe suddenly started producing giants. They appeared because the survey finally reached the depth required to pull them out of the noise. Think about what that implies. If 2 of the largest structures ever discovered showed up within the same survey, within the same 2-year window, the reasonable conclusion is not that the universe produced 2 exceptional objects close together in time. The reasonable conclusion is that there are more. Many more. The catalogue of known giant radio galaxies is almost certainly incomplete. not by a small margin, but by a significant one. Every structure that has held a record so far has been found at the frontier of current sensitivity. That frontier is still moving. As it moves, what sits just beyond it is a population of objects that existing instruments have not yet seen clearly enough to measure, classify, or name. This is what astronomers mean when they say that Porphyrion may represent a class rather than an exception. The individual object matters less than what its existence signals about the population it belongs to. If jet systems 20 million light-years or more in extent were rare anomalies, you would not expect two of them to appear in the same survey within months of each other. What you would expect instead is exactly what has happened. A trickle at first, then a steadier flow. As survey sensitivity increases, and more of the sky is mapped at the right frequencies. The question shifts from whether these giants exist to how many of them exist and what role they played in the early universe. The search for more of them is already underway. LOFAR continues operating, and its 2-meter sky survey is far from finished, mapping the portions of sky it has not yet covered. The resolution and depth of the survey are being pushed further with each data release. Researchers are also combining LOFAR data with observations from the giant Metro-Wave Radio Telescope in India, which operates at overlapping frequencies and provides a different angular resolution, filling in structural details that LOFAR alone cannot fully resolve. The Square Kilometre Array, currently under construction in South Africa and Australia, will eventually come online with sensitivity and sky coverage that dwarfs anything currently operational. When it does, the list of known giants will almost certainly grow faster than individual researchers can keep up with. What makes TXS 0033 plus 252 particularly interesting beyond its raw size is how little is known about it compared to Porphyrion. Porphyrion was confirmed using Keck observatory spectroscopy to pin down the redshift of its host galaxy and lock in its distance of 7.5 billion light-years. The host galaxy was identified. The physical dimensions were calculated carefully. With TXS 0033 plus 252, the measurement of 8 megaparsecs is an estimated figure, and the confirmation work that OEI's team did so meticulously for Porphyrion has not yet reached the same stage of completeness. That is not a criticism. It is simply the state of a fast-moving field where the rate of discovery has outpaced the rate of follow-up observation. Each new object found requires telescope time, careful distance confirmation, host galaxy identification, and detailed structural mapping. There are only so many large observatories, and the queue is long. This lag between discovery and full characterization is itself a feature of the current moment in radio astronomy. Survey instruments are cataloguing faster than follow-up instruments can confirm. This means the true census of giant radio galaxies is both growing and unresolved simultaneously. Researchers know the objects are there. They can see the radio emission. Pinning down the physical properties precisely takes longer. The lesson embedded in this is that any figure given for the largest known jet structure should be understood as provisional. The list of candidates is sitting in existing survey data right now. Some of those candidates will turn out to be projection effects or measurement artifacts. Others will hold up. A few will be larger than anything currently confirmed. What this means practically for the science is that the cosmological models being built to account for Porphyrion scale feedback are already being stressed before those models are finished. If giant jets were not rare in the early universe but common, then every simulation of galaxy formation and large-scale structure that treats black hole feedback as a local effect is missing something. The revision required is not a minor correction. It is a structural change to the assumptions baked into decades of modeling. That revision is happening now, in real time, driven by a string of discoveries that began with Alcyones 2 years before Porphyrion and has not stopped since. The record keeps moving not because individual astronomers are getting cleverer, but because the instruments are finally sensitive enough to see a population of objects that was always out there, always enormous, and always invisible to previous generations of sky surveys. Step back from the numbers for a moment and look at what this whole thing actually means. Before Porphyrion, the working assumption in extragalactic astronomy was fairly clean. Black holes shaped their host galaxies. Powerful ones shaped their galaxy clusters. That was roughly the boundary of their influence, and it was already enormous by any human measure. Porphyrion erased that boundary. A single black hole, sitting at the center of a galaxy 10 times the mass of the Milky Way, produced jets that crossed the filaments of the cosmic web itself. Not the neighborhood, not the cluster, the web, the large-scale architecture of the universe. That is the revision that Porphyrion forced onto the table, and it is not a small one. What made this discovery land differently than a typical record-breaking announcement was what it implied about everything we had not yet found. Porphyrion was not sitting alone in a category of one. Within months, TXS 0033 plus 252 came in slightly larger. Before Porphyrion, Alcyoneus had held the record. Both of those structures came from the same survey, within 2 years of each other. That pattern is not noise. That is a population revealing itself. LOFAR opened a frequency window that previous radio telescopes could not match, and inside that window giants had been waiting for decades to be counted. Astronomers are now working through the assumption that jets at this scale were not rare aberrations in the early universe. They may have been common enough to have shaped which galaxies grew, which ones stalled, and where the filaments of the cosmic web ended up drawing their lines. This matters in a very specific physical sense. When a jet 23 million light-years long pumps energy into the surrounding gas, it heats that gas. Heated gas does not collapse. Gas that does not collapse does not form stars. Spread that effect across the filaments connecting galaxy clusters, running it for hundreds of millions of years, and you are no longer talking about the evolution of one galaxy. You are talking about the conditions under which entire neighborhoods of galaxies either thrived or didn't. If jets like Porphyrion were operating across the early universe in significant numbers, then the distribution of galaxies we can see today, the clusters and voids and the strange emptiness of certain regions of space, may carry the mark of that energy. The cosmic web may not be purely gravitational in origin. That is not the story astronomers were telling 10 years ago. The catalogue will grow. That much seems nearly certain. Every improvement in survey sensitivity at low radio frequencies will pull more of these structures out of the data. Some will be smaller than Porphyrion. Some may be larger. The question of where the actual ceiling sits, how large a jet can physically get before it loses coherence or runs out of fuel or simply disperses into the surrounding medium, has no clean answer yet. The theoretical upper limit is not well constrained. What Porphyrion demonstrated is that the previous estimates of that ceiling were too low by a significant margin. The models are being revised, and they are not done being revised. There is something else worth sitting with here. The light from Porphyrion that reached Earth in time for Martino A and his team to measure it left its source 7.5 billion years ago. The universe was roughly half its current age. The filaments of the cosmic web were more compressed. The galaxies were younger, more gas-rich, more chaotic. That is the moment we are seeing when we look at Porphyrion. Not now. Then, the host galaxy that produced those jets has had 7.5 billion more years of history since that light departed. It has aged. It may have merged with other galaxies. The black hole at its center may have exhausted its fuel supply and gone quiet. The jets themselves may have long since faded, their plasma dispersed into the intergalactic medium, their lobes dissolved into the background hiss of the cosmos. We cannot know any of that for 7.5 billion years. This is not a poetic observation. It is a genuine epistemic constraint. Everything we know about Porphyrion is a snapshot of something that happened before Earth existed, before the Sun existed, at a point in cosmic time when the atoms that would eventually form this solar system were still scattered across whatever star clusters had not yet assembled them. The galaxy we are looking at is a fossil. It is a message that took longer to arrive than the age of our planet. And the message says, black holes can do this. Black holes did do this. Whether they are still doing it, whether the jets are still active, whether the host galaxy still has an active nucleus at all, those are questions we simply cannot answer from this distance and this moment in time. The field right now is in the middle of something. LOFAR's survey is ongoing. Other low-frequency instruments are being developed. Each pass over the sky with greater sensitivity will add new objects to the list. Some researchers think that when the full catalogue is assembled, jets at megaparsec scales will turn out to have been a defining feature of the early universe. Not an exception, but a norm. That would mean the universe was, at a certain epoch, threaded through with structures like Porphyrion on a scale we have barely begun to map. The reckoning with that possibility has started, but it is far from finished. Whatever the host galaxy of Porphyrion looks like today, in the universe as it exists in this moment, the light carrying that information is still in transit. It has been crossing space since before the Earth formed. It will not arrive for another 7.5 billion years. The jets are out there, invisible to us, doing whatever they are doing 7.5 billion years later, and the news is still on its way.